and graph complexes, please.
Okay, thank you. Well, this is the last talk of the conference, and it's traditional for the last speaker to lead a round of applause for the organizers. So we should clap for them.
Thank you.
And actually, they did a remarkable job. I mean, considering the pandemic and the delays and all of the accidents that prevented people from coming, from COVID to broken knees, etc. Thanks for doing this. I think it was really interesting, and yeah. So
let me just forward the thanks also to Paul Boldow, who sort of got hijacked and to help here, and without him, this all wouldn't have been possible. So thank you, Paul.
Well, let's not forget Marco, too. Right. Great. So the last talk of the conference, I'm probably not going to say anything new, but I just want to give a sort of a point of view on all of this graph complexes stuff. So what's my point? So graph complexes are generally defined as chain complexes, so they're algebraic objects. But if you're a low-dimensional topologist like me, what you use chain complexes for is to understand topological spaces. So we like to think of chain complex as some complex associated to a topological space, like simplicial chains, especially, or CW chains. So what I want to do is start seeing graph complexes as simplicial or cellular chains. For some space. When I do that, I can feel grounded. You know, I know what I'm studying. I'm studying something I can put my finger on. Right. So graph complexes are complexes whose generators are graphs. So these should be spaces of graphs. So I want to, in this talk, I'll probably only mention the commutative, associative, and Lie graph complexes, the classic ones by Kontsevich. Commutative, associative, and Lie graph complexes, but you can tweak these, and I'll mention every once in a while what you do in slightly different situations. Okay, so to start, I want to start with a space of graphs I've been studying for a long time. It's a space of marked metric graphs called outer space. Whoops. Right, so this is going to be a space of graphs. So what do I mean by a marked metric graph? The terminology marked is a little unfortunate because there's the idea of a marked point on a Riemann surface, which is different from what I mean by a marking. So for me, what's a point of this space? Well, it's a pair consisting of two things. G here is a finite connected graph. And I want all vertices, let me say, write this. are supposed to have valence at least 3. So here's an example. Here's a graph. It's got a vertex of valence 3 up there and a vertex of valence 5 down there. And so that's a graph, but it's supposed to be a metric graph. So the lengths on the edges L sub E, L1, L2, L3, L4. And I want these to be positive real numbers. And often it's really irrelevant what I can scale them all and not think of the graph as very much different. So I often assume, in fact, in this talk, let's assume the sum of the edge lengths is 1. So if I just take a graph and multiply and measure in meters instead of feet, it's the same graph. The numbers change, but it's the same thing. Okay, so that's what G is, and what's little g. This is a map from a rose to G. What's Rn? Rn is a rose with n petals. And this map is not just any map, it has to be a homotopy equivalence. In particular, it induces an isomorphism on the fundamental group. And on H1, etc. Okay, so that's what a point is, that's what the little g and big G are, and when are two such objects the same thing? Well, it's not supposed to depend on how I draw them in the plane. In other words, if I have, so G is going to be equivalent to G prime if there's an isometry from G to G prime. Notice that when I put lengths on the edges of the graph, I made the graph into a metric space with a path metric. So there's an isometry from G to G prime that commutes with the markings up to homotopy. So if I had another graph here, if I had an isometry here, maybe I would I could switch edge L1 and L2, and then the lengths would look like that. But there's an obvious isometry, and if I compose those two, I actually get the same, another map. So this is G and this is G prime. Those are the same point. It doesn't matter how I draw this guy in the plane. It's the same point. Okay, so I guess I was thinking last night, I think I've explained what outer space is maybe several hundred times at least. And I'm sorry, I'm sure some of you at least have heard this before. So but that's what it is. Okay, so that's outer space. Let me just here mention one variation. So I started with a graph with no legs, but I can make the graph have legs. Or depending on who you are, you might call these leaves, or you might call them hairs, whatever, or you might call them infinite rays. well, let's leave it at that. That's enough words. So you can certainly do that. And then you can look at a space, let's say an S, that's points GG, where G is connected. The fundamental group is isomorphic. The G gives an isomorphism of the fundamental group of G, well, to Rn, but to F, the free group of rank N, and G has S legs. But there's the only thing you have to do different is instead of, so this is, Ben mentioned this in his talk. Instead of the rows, this, you take the rows with S thorns, and you can either label them or not. Let's label them. You get different spaces. And then you need a homotopy equivalence to the graph, which now has legs. But you don't want just any homotopy equivalence. Whoops, this has 3 legs. 1, 2, 3. You want G of the ith hair has to go to the ith hair leg. So you don't look at all homotopy equivalences, you just look at homotopy equivalences that send the numbered endpoints there to those numbered endpoints of G, 1, 2, and 3. Okay, so everything I'm saying can be done for graphs with legs as well as graphs without legs. Okay, so that's a set of points. Well, how do you make it into a space? Well, what I'm going to do is to every, actually there are many ways to say this. One way to do this is we have a marked graph. I want to associate that to that a simplex. So several people have mentioned how you do this. I'm going to do it too. Let's see. There's a graph. And here's a simplex I'm going to associate to that graph. So the simplex is 3-dimensional because my graph has 3 edges. They've got lengths L1, L2, and L3. So and the sum of the lengths is equal to 1. So that corresponds to a point in this simplex, L1 plus L2 plus L3 equals 1. Of course, I have a marking too. And varying the lengths on these edges doesn't affect the marking at all. So this whole blue simplex is a simplex of marked graphs. And there are face maps, face relations. You have sigma of G has a face tau of G sub E, G sub E, where to get to this face, what do? You take, if I let this length, the middle length here go to 0, I go to the edge L2 equals 0 in this picture. And with L2 is equal to 0, then the graph looks like a rose. And that's a face of the simplex. There's another face when, say, L1 equals 0. That's this green face. That corresponds to the graph where the L1 loop has been shrunk to a point, and all I've got left is that. Now, that's fine. That's not a point in my outer space. None of those green points are actually in my outer space because the graphs don't have rank n. However, you might recognize this as a stable tropical curve where you just put a 1 at that point. And at the ends of these vertices, you have, none of the vertices are actually in outer space. And in fact, in this graph, none of the vertices and those two edges are not actually in outer space, but they form a part of a, so I was going to say, this simplex is a face in this simplex if E is a non-loop edge and map G to GE collapses E. We had a marking and you have this collapse, and this is you get an induced map on marking on the collapsed graph. So I'd like to point out that when you do this, if I take, say, let's take a different graph. There's another one with 3 edges. Somehow I had more space when I was making this talk than I do now. There's a graph with 3 edges, so that corresponds to a triangle, X and Y. And when I when I collapse the middle edge, say, I get this edge where the graph has an X and a Y like that. But notice that this graph is the same as the graph if I flip, say, the Y edge, because there's an automorphism of that graph that flips that edge. There's an isometry of that graph that flips that edge. So this I can think of as an edge of a different simplex. This one. So this edge in the middle is the face of both of those simplices. And in fact, if this edge happened to be marked XY, then this edge would be a face of all 3 of the simplices that I have in my picture. Yeah. Okay, so let me show you what happens for n equals 2. And I've got no leaves. So this is a picture of outer space in rank 2. If you get the AMS notices, you've seen this picture, at least if you read the AMS notices, there was a what is outer space article at that point. Oh yeah, right. I forgot to mention the fact. So the fact is that there's a theorem that says this outer space is contractible. And Alan Hatcher proved in 1995, I think, that all of these CVNSs are also contractible. And I haven't told you what the star means yet, but I will. Okay, so here's outer space in rank 2. You'll see the 3 simplices that I drew on the last page. There's that one. Well, this is the first one I drew, the yellow one, and then there's that one. So there's 3 simplices there, 1, 2, and 3 that are stuck together. You can see lots more simplices. You notice on this picture that I've labeled the complement of a maximal tree with some words in the free group. And those words are a basis for the free group. So that's one way of saying what the marking is. And you can think of, yeah, that's one way of saying what the marking is. Right. So let me talk about the simplicial completion. Let me grab this. Well, maybe I'll just put it on this page. Whoops. Simplicial completion. So as I pointed out, lots of these faces of these simplices are not actually in outer space. None of the vertices are in outer space. And actually none of the top edges of the yellow triangles are in outer space. So there's this whole green business, which is a subcomplex, which is not in outer space. Well, it's not a complex yet. So the simplicial, what's the simplicial completion? Oh, I'm sorry. I didn't finish telling you what the topology was. I told you how you get a simplex associated to a graph, and I told you what the face relations are, but I didn't tell you what the whole space was. So CVN is the disjoint union of all these simplices sigma of G modulo the face relations. So it's just a quotient space with the quotient topology. Right. So what am I going to do to get the simplicial completion? Well, I'll take the disjoint union, not of these open cells, but of their closures. And I have to go modulo face relations. So in that case, I get the picture that you actually see here. All of those simplices I think of as closed simplices, and this is a simplicial complex, which I denote by putting a little star. Okay, so that's outer space, and that's a picture of what it looks like in rank 2. And that's the simplicial completion, CVN star. And I also want to notice that the subcomplex at infinity, this green stuff, is a subcomplex. So this is simplices in CVN star minus CVN. That's a subcomplex. The way you can see that is simplicial, the whole space CVN star is a union of these open simplices, and the things that are at infinity and are not actually in CVN, those are the faces you get by collapsing a graph that has a loop in it. And if you've collapsed a subgraph with a loop in it, then further collapses are not going to change the fact that you've killed some fundamental group. So all the faces of a simplex at infinity are also at infinity, and so you have a subcomplex. One more space I want to mention is called reduced outer space. If you look back here at outer space, those yellow simplices seem kind of unnecessary. They're just sticking up out of the blue sea. They're like shark fins. So if you can just shrink all of the separating edges uniformly to points, and all those sharks go back under the water, and you get what something's called reduced outer space. This is the union of sigma of G modulo face relations, where G is one particle irreducible? So this is a picture for n equals 2. The sharks have gone underwater. So notice that there's a simplicial completion of this too. So this shrinking business, deformation retracts CVN to reduced CVN. But CVN star does not deformation retract to reduced CVN. And that's basically because when you shrink all of those guys into the water, there's no way to say where the vertex should go. There's no natural way to say where the vertex should go. It's not really a problem for n equals 2 in this picture, but yeah, it's different. Okay, so why was I studying CVN in 1986? Because the group of I was studying the group of outer automorphisms of the free group, and that acts on this space. And the way to realize that is that if you take a homotopy equivalence of the rows, you notice that induces an isomorphism on fundamental groups. In other words, it induces an automorphism of the free group, and homotopy equivalences give you the same map on pi1. So out of Fn is actually the group of homotopy classes of homotopy equivalences of the rows. So if I have a point in outer space, and I've got an element of this group out of Fn, I can realize it as a homotopy equivalence of the rows. Maybe so I'll give it the same name. And then if I compose this map with my old map, I get a new marked graph. I get a new point in outer space. The only difference from the old point is the marking. It's exactly the same graph. It's just got a different identification of its fundamental group with the rows. So this gives an action of out of F on this space. The stabilizer of a point, the stabilizer of point GG, well, I need G of alpha to give me the same point in outer space. So I need there to be an isometry between G and itself that gives me, that induces this map. So I can identify the stabilizer of any point with the group of automorphisms of the graph. So as we saw, when I flipped the edges of the rows, I still had the same point in outer space. That corresponds to the automorphism of the fundamental group that takes Y to Y inverse. Okay, so that's outer space and that's its action. Since we have a group acting on a space, we have quotient spaces. MGN is called the moduli space of graphs. And MGN star has a new trendy name called the tropical moduli space. Moduli space of tropical curves. Okay. So what do I get out of this as a group theorist? Well, the fact that outer space is contractible and the fact that it acts on this out of Fn acts on this space with finite stabilizers tells me from basic algebraic topology that the cohomology of this group is isomorphic to the cohomology of this moduli space of graphs. So, and right, and let me just remark that, so this was all thinking of out of Fn as the homotopy equivalences of the rows. If I look at pi naught of homotopy equivalences of the rows with S thorns that fix the thorns, I get another group. Let's call that ANS. And whoops, the cohomology of MG and S computes the cohomology of that group. Okay. So where do we go from here? Yeah, okay, so that's that. I've told you some spaces of graphs. What's this got to do with graph complexes? So the easiest relation to draw is between the commutative graph complex and outer space. So I've got the simplicial closure of outer space, that's the simplicial complex. The subcomplex of stuff at infinity is a subcomplex, as I pointed out before, and it's invariant under the out of Fn action. Remember, the out of Fn action doesn't change the graph at all. It just changes the marking. So if I look at the quotients, I've got CVN infinity. The quotients are contained in each other, and they've got a relative chain group. So let me try to explain what this chain group is.
Karen?
Yeah.
What is the CV bar? I thought the star already glues the infinity.
Yeah, no, I meant the quotient. Sorry.
The overline.
Yeah, this is the quotient. CVN bar is CVN mod out of Fn. Sorry,
Oh, yeah.
I already gave it a name, didn't I?
Oh, thanks.
Yes, I did give it a name, Mn star. I didn't really talk about M in infinity. Yes, sorry, thank you. Right. Mn star is CVN modulo out star mod out of Fn. And same thing for infinity. Right. So I want to, so what does the action of out of Fn do? It just changes the marking. It does that transitively on simplices. So I get right. Trying to explain what CVN star is. So if I take, let me think upstairs instead of downstairs. So upstairs, the chain complex giving the relative homology is generated by these simplices, which are indexed by marked graphs. And the boundary map of GG is G sub E. G sub E is a sum over E. Now, if E is a loop, that's not an outer space, that's at infinity. So the G sub E, this term is 0 if E is a loop. So I could think of this as a chain complex generated by pairs GG, and the boundary map collapses edges that aren't loops. What about, but that's upstairs. Downstairs, the boundary map goes to the boundary map still. So I still have this feature that if I can only collapse edges that aren't loops. But downstairs, what does the chain complex look like? Well, it's generated by, so I said that the automorphism group acts transitively on simplices. So downstairs, I can just forget the marking and just look at this. I just get one, I get something, a quotient of this cell for every graph, isomorphism class of graphs. And the stabilizer is the automorphism group of the graph. And then it's a simple exercise to see that this quotient graph is a cone on, well, oh yeah, one other thing I want to say upstairs is these are simplices, right? But the vertices of the simplices correspond to the various edges of the graph. So to make this a simplicial complex, I actually have to orient the simplices. So an orientation is given by an ordering of the edges. Okay, this should be beginning to look familiar to you. Now downstairs, what do I have? I've only got one cell, one piece of my quotient for every isomorphism type of graph, and it gets folded up by the group of the automorphisms of the graph. But that's something that's easy to analyze. It's a cone on either a rational homology disk or sphere. So it kind of looks like up to homology, as far as homology can tell, it's either going to be a cone on a disk or a cone on a sphere. In other words, it's going to give either a real cell or it's not going to give a cell. And how can you tell whether it's going to be a cone on a disk or on a sphere? If there's an orientation reversing automorphism, then the quotient is going to be a cone on a disk. So it won't contribute anything to the homology of the resulting space. If not, if there's no such alpha, the quotient is a cone on a sphere. So it gives you a genuine generator in homology of in rational homology of the chain complex. So let me put all of this information together. What is C star of, I'm going to use the same notation, CVN bar star, CVN infinity bar. It's has one generator for each graph with no odd automorphisms. and the boundary map collapses non-loop edges. So you will recognize that as exactly the commutative graph complex. CG, what do we call it? G, in rank n, the n, the yeah, for graphs of rank n. Okay, so there's a, so I've succeeded in realizing the commutative graph complex as a chain complex, a relative chain complex on a topological space. And so this is actually a justification for the term orbifold Euler characteristic. I mean, you think of an Euler characteristic as Euler characteristic of, so what's an orbifold? It's an orbifold that locally looks like a manifold modulo of group action. And this has been generalized to the idea of cell complex modulo a group action. Here we have a whole cell complex modulo a group action. So it's natural to talk about its orbifold Euler characteristic, which is just the sum of the cells divided by the sum of the cells of dimension I divided by the order of their stabilizers. So this is what Michi and I this is right. This is what Michi computed. The orbifold Euler characteristic, and Kontsevich has also computed, and many other people have computed the orbifold Euler characteristic of the Lie graph complex. This is why it can be called an orbifold Euler characteristic. That's just a side remark. Okay, so that's the commutative graph complex. I also wanted to talk about outer space and the Lie graph complex. Yeah, I wrote this late last night. I said, a generator of the odd Lie graph complex is a fearsome beast. So it's got a lot of parts to it. What is it? You have a graph with an odd orientation. So an odd orientation can be thought of as ordering the vertices and orienting all of the edges. That's one manifestation of an odd orientation on a graph. But then you don't just have that, you have into each vertex of the graph, you have to plug an equivalence class of trivalent planar trees. And the equivalence is modulo antisymmetry and IHX relations. In other words, a generator of the Lie operad, it has to get stuck into each vertex. So what does that look like? There's one. Okay, there's an odd graph, and a you have to stick these things into the vertices, planar trivalent trees. Those correspond to generators of the Lie operad. So it looks like maybe like this after you stick them in. Okay. However, there's a way to sort of tame the beast. Instead of thinking of Lie graphs with all of this data on them, you can think instead of something called forested graphs, where a forested graph takes your Lie beast and looks instead just at the graphs that are inside the trivalent trees that you attach to the vertices. So I claim that there's a way to associate to each Lie graph something which I call a forested graph. So a forested graph is a trivalent graph with some forests in it. And a Lie graph has all this orientation data, and the orientation I'm going to give on my forested graph is an ordering of the edges of phi. Okay, so I can make a complex out of these. Yeah. So how do I take the boundary in the Lie graph complex? I take these two vertices up here, that one, and I'm supposed to contract non-loop edges in the original graph. So here are the non-loop edges. There's that one, and that one. And what do I mean by contracting the edges? Well, I have to I just stick them together, and I perform the operad operation, which merges both of these operad elements into a single guy. So you can see that what mimics that in the picture on the right is taking a forest and adding an extra edge to it. So the boundary of this graph that I had up here is is given by all possible ways of adding an edge to the forest. Okay, so this is not the forested graph complex yet, because I haven't taken into account the IHX relations. But what is an IHX relation? Well, this is, let me call this complex with this boundary operator FG hat star. And I'm going to look at IHX contained in FG hat star. Well, IHX is generated by things that look like this. I'm going to need more space. I didn't want to lose that, so maybe I'll just move it to another page. So what's IHX? Well, whenever I have when I ever have a piece of a graph that looks like three graphs that look like this, the thing that distinguishes these three graphs in this picture, these are just pieces of graphs. The thing that distinguishes these three graphs is if I contract E, I get the same thing. And this is the graphs are drawn suggestively here to suggest the traditional IHX relation in the Lie operad. So IHX is generated by sums G1 plus G2 plus G3. And I'm going to define the forested graph complex. Fg star is the quotient of F hat G star modulo this subcomplex IHX. And the theorem is that this is exactly the Lie graph complex. So this is, I mean, should be clear. The problem, of course, as always, is the signs, getting all of the signs right. But it's true. Okay, so that's the forested graph complex. And I claim it's the same as the Lie graph complex, but what does this have to do with outer space? So the next few minutes, I'll try to tell you what forested graphs have to do with outer space. Let's go back to our picture of the simplicial closure of outer space and take its barycentric subdivision. So instead of this, I'm going to take the barycentric subdivision of each of these guys. I'm not going to be able to draw very much of it. Okay, so that's a picture of the barycentric subdivision. It goes on, of course. And now I'm looking at inside of there, I have the barycentric subdivision, of course, of the boundary complex. And I'm going to define Kn to be the subspace of the barycentric subdivision spanned by the vertices that are in that aren't at infinity. So this vertex is not at infinity. This one isn't. This one isn't. All of these are. Those are all at infinity. All those guys are at infinity. This one isn't. This one isn't, etc. Whoops, those were blue. So spanned by the blue vertices, I just get some of the barycentric subdivision, the subcomplex, and that's called the spine. So if I forget the simplices at infinity, maybe it's easier to draw a picture of it. So I barycentrically subdivide this. Anyway, I claim that what I'm going to get looks like this. So I've left off the part corresponding to the shark fins. But now you can see why I called it the spine, because it looks like a spine. Okay, so that's Kn. Spine of outer space. So Ralph mentioned a construction like this in his talk. He also called it a spine. And it's obvious that all of CVN deformation retracts to the spine. This is not true of, again, this is not true of the simplicial closure. It does not deformation retract to the spine, but outer space does. The point is that every simplex has some vertices at infinity, and you just push in linearly from those vertices to the vertices that aren't at infinity in the barycentric subdivision. But the fact that there's a deformation retract implies that Kn is contractible too. Right. And what's the chain of what's a K simplex in the spine? Well, it's a chain of K forest collapses. That's how you get a barycentric subdivision. You take you go to faces, K faces at a time. So let's try that. Here's an example. There's a graph. I collapse that edge. I get to that graph. I collapse that edge. I get to this graph. And there's a vertex in, these are all marked, of course, by G. And yeah. And as Ralph pointed out, I collapsed the green edge first, and then I collapsed the blue edge. The blue edge lived here. I could have also collapsed the blue edge first, and then the green edge. So that would have given me this. And so the point is that this K simplices naturally arrange themselves into cubes. And how do I say what the cubes are? Well, I just take my graph and I say what forest I'm going to collapse. So now you see forests. Cube is a pair consisting of a graph and a forest. And of course, never forget the marking. And the boundary map is a difference of there's two kinds of boundaries to this cube. There's so I can think of the left-hand edge here as collapsing the blue edge, which turned green. And I can think of this edge as, yeah. Sorry. Is collapsing that. So what am I going to say? What am I saying? I'm trying to say, I can recognize this edge as the same graph, but the forest has one less edge. And I can recognize this edge as a different graph where that edge has been collapsed. So the boundary map is sum of two boundary maps, boundary collapse and boundary remove. C collapses an edge of phi, and R removes one. Okay, now I have exactly 2 minutes. I'm about halfway through my talk, but don't worry, I won't go over. It's the last part of the last talk of the conference. So at least you can see a glimmering here now. We've got graphs and forests. That's what we had when I massaged this Lie graph complex into a forested graph complex. And the theorem is that there's a way of making this into, of identifying the homology of the forested graph complex with the cohomology. There's a homology cohomology shift of the quotient of the spine modulo out of Fn. Right. So then this slide was going to tell you how to do that, but yeah, don't want to say that. But let me point out that as a corollary to this theorem, so we had the homology of the forested graph complex is the homology, Lie graph homology. In rank N. And I'm saying that that's the cohomology of Kn mod out of Fn. And since Kn is contractible and out of Fn acts with finite stabilizers, that's the cohomology of the group out of Fn. So so it's not hard to finish this to show that the cohomology of out of Fn is the same as the homology of the Lie graph complex. And that's a way to think of the Lie graph complex. And this is what Michi and I used to this version of, we computed the Euler characteristic of out of Fn by computing the Euler characteristic of the chain complex for this quotient space, and by what I've said, which is a fact due to Kontsevich, in fact. This is the cohomology, the homology of the Lie graph complex. Okay. Yeah. I'm not gonna talk about this. I'm gonna tell you what I would have talked about if I had infinite amounts of time. So Francis has made great use of this tropical Torelli map. And I was going to tell you that there's a really easy way to understand what this is in terms of outer space, because there's a map from outer space to the symmetric space that's invariant under the out of Fn action that commutes with the out of Fn action and the GLNZ action via the natural map from out of Fn to GLNZ. So that gives you, this is called the Jacobian, because when I invented it, I had no idea about anything in algebraic geometry. And if you look at the induced map on the moduli spaces, well, it maps this, yeah, no time to talk about this, to positive definite quadratic forms, mod SLNZ. This is the tropical Torelli map. And then with more infinite amounts of time, I was going to tell you about how to think about graphs as sphere complexes. And then I was going to talk about the bordification of out of Fn and of outer space and duality. And obviously I don't have time to do any of that. So thanks for listening.
Thanks for your talk. Questions and remarks. Francis, please. I see your name filling up here.
I was clapping in admiration. I
Right.
don't have a question. Thank you.
Okay. Then questions and remarks, please.
So Karen, in your last theorem, you had these two forested graph complexes.
Mm-hmm.
So, and one has only trivalent graphs, right?
Yes.
But the other does have higher valencies.
Yes.
Yeah.
So these chain complexes are definitely different.
Yeah.
Right. You need you have two boundary operators, one which collapses edges and one which removes edges from the forest, right?
Yeah.
Now we're looking at cohomology, so you can think of that as adding edges to the forest or splitting vertices and adding the new edge that you get to your forest. So you start with a graph that is not trivalent, and you start splitting all those vertices by adding little trees in them. And turns out that the space of trees is easily seen to have no homology except in the top dimension, which is where you've split all of the vertices into trivalent vertices. So all of that homology that seems to be there from the graphs that aren't trivalent goes away when you pass to homology. Yeah.
Yeah, might be just a coincidence, but it kind of looks like one of these relations in quantum field theory where you can resolve higher valent vertices into linear combination of lower vertices. I don't know, Dirk knows a lot about this, like this Ward Takahashi.
I don't think there's a coincidence here. I actually do think that many of the things which Maxim did with the Lie algebra and whatever Lie comes precisely from his own work long ago on quantum field theory. It's just looking at what you do in quantum field theory with gauge theories, really. Because basically at every vertex, every 4-valent vertex is blown up into 2 3-valent vertex. And every 5-valent would be blown up into a 4-valent, into 3-valent, and therefore into 3 3-valent, and so on and so forth. And this goes back to Cvitanovic, who started Lie algebra representations theory on graphs, just coming from that. So, and many people doing very similar things.
Yeah, well, that's interesting.
Mm.
Yeah. Yeah, I didn't get to say the words quantum field theory in my talk at all.
That's fine. You did a lot of quantum field theory, in my opinion.
Yeah. I'm still trying to learn it.
It's a language thing. More questions, remarks, please.
Yeah, may I ask 2 questions? This is really enlightening. I think my first question is probably a silly terminology question regarding the definition of the Lie graph complex. I understood that you stick in each vertex a planar trivalent tree, but then when you drew the IHX relation, I saw a tree with a crossing in the plane. So what does planar mean?
Well, remember my trees are not, so that was I could have undone the crossing. Where was I?
So you use an IHX relation to undo all your crossings?
No, you don't need to undo anything.
Okay.
I just drew it like that so it would look like an X. Did I do this? Oh yeah. Okay, so this is just if you want to do it as a planar tree, it looks like C, D, E, A, B, right? But the way I drew it, the A, B, C, and D are so all I'm talking.
Oh, I see. Okay.
So
you just care about like the sort of cyclic order of
right.
the outgoing edges at each vertex.
So the fact that the A and B got switched here, it's responsible for the fact that there's no minus sign here. So normally IHX is I minus H plus X. I don't know if you know IHX relations.
So when you say planar, sorry, I'm so fixated on this. When you say planar trivalent tree, you mean you didn't happen to draw it in a planar way this way, but you could communicate.
Right.
Like,
all I mean is that there's a cyclic order around each vertex.
Okay, great.
Yeah.
And my second question, it's about something that you said just in passing, again regarding orbifold Euler characteristics. Were you like, does the, e.g. the orbifold Euler characteristic of the commutative graph complex, is that telling you something precise about outer space or no?
I don't know. I mean, Kontsevich said he was gonna, he had a very brief paragraph about the orbifold Euler characteristic. And the question is, which was just, the sum of the, the order of the graph divided by the automorphism, the number of edges of the graph divided by the cells corresponding to the graphs divided by the order of the automorphism of the graphs. And the question is, why is he calling this an orbifold Euler characteristic? To talk about an orbifold, you need some sort of a group action somewhere, either a local group action or a global group action. So it was just a matter of explaining the terminology and trying to divine what was in Kontsevich's head, which is sometimes a lot of work. Yeah. So this terminology about orbifold or virtual Euler characteristics comes up for group actions on cell complexes, group actions on manifolds, which are locally quotients of spaces which are locally quotients of manifolds by group action, but there's always a group in there. So, yeah. And the orbifold Euler characteristic of a group is a really interesting number. It's a rational number, and it has deep relationships to number theory. Yeah.
Further questions or remarks? If not, I think we should repeat this conference in 1 or 2 years to listen to the second half of Karen's talk. It would be very nice. And let's thank Karen again.
All right.
And
Okay, well, thank you. Thanks, everybody.
thanks, everybody. Yeah.
I'm really sorry I'm not there.
Yeah, me too.